In this video, we're going to go over confidence intervals, specifically for a mean. There are other confidence intervals that you can do, but we're going to just go over when you have one sample and you take the mean of that sample and you want to make a confidence interval. So what is a confidence interval? A confidence interval is a range of values that estimate the population parameter based on the sample statistic. So remember, a population parameter is some kind of number in the population, and a statistic is that same kind of number but in the sample. So remember, we're doing inferential statistics. We don't have the population parameter, but we want to try to estimate it using the sample statistic. So that's our next best thing, because we don't have the population parameter. So we're going to use the sample statistic to estimate the population parameter. So for example, you might hear in political polls that some candidate is up by between 2 to 4 percentage points in the polls, or whatever amount they're up by. For this class, we're going to start with estimating the population mean with the sample mean. So notice in my political poll example, I didn't say they were up by 3 percentage points, right? I gave a range of numbers. So it was between 2 and 4 percentage points. And that's because we have a sample mean, or sample percentage points. We don't have the actual percentage points, right? So when you have these political polls, they don't survey everyone who's going to vote, right? They sample a subpopulation of that potential voters. So they can't be certain that that's how much the candidate is up by, but they can make a kind of educated guess, and that is the confidence interval. So they have this range between 2 and 4 in this example. So in the middle of this confidence interval is 3. And on each side we have a margin of error of 1. You might hear that as well on the news. When they say margin of error, they mean the margin of error in a confidence interval. So the middle is 3, and that's the sample statistic is 3 percentage points. We have a margin of error of 1 percentage point. And why we have a margin of error is because the sample statistic isn't going to be exactly the population parameter, unless we just got really lucky. And I mean, it could happen, but we're not really sure if the sample statistic is the actual true population parameter that we're trying to estimate. And that's because we have sampling error. And that's the variability in the sample means just due to chance, or in the percentage points just due to chance, depending on what sample you use. So the sample mean will not be the same as the population mean, and the smaller the margin of error, the more precision we have. So we want a small margin of error, right? If I say this person's up by between 2 and 4 percentage points, that's more informative than if I say they're up between 10 and 50 percentage points. I mean, that basically tells you nothing, right? Well, it does say that they're up and they're winning, and probably by a lot, because 10%'s a lot. But it doesn't tell you very precisely how much they're up by. So we want a smaller margin of error, but we do have to have this margin of error because we're getting information from the sample, and the sample statistics are going to vary just by chance. Okay? And it's not going to directly reflect the population unless by luck you do get the exact same number, but that's probably not going to happen most of the time, and we won't know when it happens. So we have a sampling error, which is the variability just due by chance, and that's why we have this margin of error. So here's a basic formula for any confidence interval that we have. We have the sample statistic plus or minus the margin of error. So in our poll example, the sample statistic would be 3 and our margin of error would be 1. And so we have two numbers. We have a lower bound and an upper bound. The lower bound is the lower number, so it's the sample statistic minus the margin of error. So in our poll example, we have a sample statistic of 3 and a margin of error of 1. So we do 3 minus 1, which is 2. And then we have an upper bound, which is the sample statistic plus the margin of error. So we have in the middle the sample statistic of 3, for example, plus 1, which is our margin of error. So we have 4. So we said that the candidate is up by between 2 and 4 percentage points. And that's our confidence interval. So a basic kind of interpretation of this confidence interval is that I estimate the population parameter to be between the lower bound and the upper bound, whatever those numbers might be. So this is a basic formula for any confidence interval, and as we go through this presentation, we will get more specifically about how to do it when we're trying to estimate a population mean. So the margin of error is based on two things. So one is the confidence level. How confident can you be in this confidence interval? So some you can be more confident in than others, right? I can make the confidence interval as big as I want or as little as I want, really, by manipulating the confidence level. So you want to make sure that you have some kind of high confidence to make sure that your confidence interval gives you some valuable information. So I could say that the candidate is either down by 100 percentage points or up by 100 percentage points. And we have a lower bound and an upper bound there, but that doesn't tell you anything. But that one would be really high confidence because it's on like 100% confidence because, well, there's no way they can't be either way. Like they either have to be up by so many points or down by so many points, and I included all the possibilities. So that's 100% confidence, but there we lose precision and doesn't tell you anything at all. Now you can have some kind of balance if you have a good enough sample. We'll get into that. Okay, let's pretend that we are making a confidence interval for a test and the average is 80 points, 80 exam points or whatever you're talking about. And I can make confidence intervals, and depending on the confidence level, the ranges will be different, even with the same sample data. The same exact data can have different ranges. So this is kind of an extreme example, but say one confidence interval has the lower bound of 70 and the upper bound of 90. So the middle is 80, and then we have a margin of error of 10 on each side, right? So plus or minus 10. And then you could also hypothetically have a confidence interval that is between 79 and 81. So here we have a middle of 80 again, and then we have a margin of error of 1. So we have 79 as the lower bound and 81 as the upper bound. The first confidence interval is not precise. It has a large margin of error of 10, but the confidence level is high. And then the second confidence interval might be very precise. It has a low margin of error of 1, but the confidence level is low. So it's just kind of a trade-off. So how precise you are and your confidence level kind of trades off. So you must declare your confidence level because you don't know what the real confidence level is unless I tell you, right? You can pick anything between, hypothetically, anything between 0 and like 99%. You can't really be 100% sure of your confidence level, of your confidence interval, but you can be up to 99% confident. And you can be as low as like 1%, I guess. But you never are going to be that low. You shouldn't do that. But you must declare it. The most common one is 95%. 95%. And so you say something like, with 95% confidence, I estimate the population parameter to be between this lower bound and this upper bound. Some other common levels are 90 and 99. So pick one of those, usually 90, 95, or 99, and the most typical one is 95%. So I kind of told you in the last slide that declaring your confidence level is important because we can have different confidence levels for the same data, and that can really distort or change your range of values that you calculate. But what does that 95% mean? Okay, so here we have a sampling distribution. Remember, it's usually kind of hypothetical because we really don't have the sampling distribution available to us when we're doing a confidence interval, because you wouldn't know the population mean, and then why would you do a confidence interval? But it's kind of hypothetical, and it's from the central limit theorem. And this is not a population distribution that I've drawn. Remember, the population distribution is the histogram of all individual values. This is a histogram of the sample means, okay? This is what I've drawn here, and I want to have a 95% confidence level, and I'm going to randomly select one sample and create a confidence interval for that sample. And this stuff is kind of going in the background, right? If I am making a confidence interval, I really wouldn't know what the sampling distribution looks like. But we have to talk about the hypothetical based on the central limit theorems, and so we kind of have these rules based on this theory. And if this theory holds true, then what I'm talking about holds true, even though we can't see it. And I know it's a weird concept, but hopefully eventually you kind of sink in, okay? So here we have a sampling distribution, and I want to have a 95% confidence level. So I want to have 95% of my sample means be between these two blue lines. And so to do that, I want to have 5% on the edges. And if you divide 5% by 2, you're going to have 2.5% over here on the left side and 2.5% here on the right side. And if I do that, then I'm going to have 90% of the sample means in the red area. Okay? So, and that big red line is the true population mean, which you're not really going to know, but it's somewhere out there. Okay? So again, the middle red percent is 95% of the sample means. And this distribution is kind of hypothetical. I don't know what it really is. I don't know what the population mean is, but I can make I can know some things about it. If I know the central limit theorem is true, I can know what the standard error is. I won't really know what the population mean is, but if I know the population, standard deviation, and I know the sample size of my sample, then I can know what the standard error is. And I can kind of know some things about this sampling distribution, which I really don't have access to, but I can use the central limit theorem to kind of know a little bit about it and enough to make the confidence interval. So say this is our hypothetical sampling distribution, and then I take a sample and I calculate its mean. So this is its mean here in this light blue here, and say that the sample mean ends up being 80. In our other example, okay? And I don't know what the red line is, which is a population mean. I don't know what it is, okay? But I know the spread of it. I know the spread, I know the standard error of the sampling distribution because I know what the population standard deviation is, and I know what n is. And so then I can say how spread out is the sampling distribution, what is its standard error, which is the standard deviation of the sample means. And this is all based on the central limit theorem. So I have to either have a normal population distribution or at least an n of 30 or more, and I have to have some reasonable assumption of random sampling, or at least it's not that biased of the sample for this to be true. Okay, so we have our sample mean of 80 here, the vertical line, and then I want to calculate the margin of error and make our confidence interval, which I have here in blue. This is horizontal line here, and say the margin of error is 10. So then we would have 70 here and 80 here. Now, I really don't know that the confidence interval is right here on the distribution. I really don't know where it's at. It could be on the right side. It could be way to the left, to the right. I don't really know. But I do know the spread of the distribution. And so what I can do is make the width of the confidence interval the right width. And so let me get a different color here, black. So this width of, oh sorry, it's purple. This width of the confidence interval is actually the same width between these blue lines that I made on the sampling distribution. So from here to here is the same width as here. So this is equal to this, okay? And if I do that, then I can have some amount of confidence. And I'll tell you in just a second what that 95% confidence level really means. So I know this is a little weird, and hopefully it kind of sunk in a little bit. So if I randomly selected the mean, and that's our confidence interval. Now again, we have the 2.5% here and here, and our 95% in there. Now, what we can do is find the z that goes with that 95%. So if I have 2.5% here and 2.5% here, if you go to the z table and look up 0.025, because we're going to put it back into proportion form, this is in percentage form, then you're going to find a z of negative 1.96. And then if you look up 0.95 plus 0.025 and look up 0.975, then you'll get a positive 1.96. So those are our z values, and this is going to determine our confidence level. So whatever we pick our z as, you're going to call the critical z, that is how we do the confidence level. So if we wanted to do 90%, we would go and make the blue lines even more in a little bit, and we would get, I think would be 1.65, which would be negative, and then 1.65 here. So you can see the smaller the confidence interval, the less we kind of cover the sampling distribution. So to get our critical z, you need to know your confidence level. So I'll say it's 95%. Now you're going to put that in a proportion form, so 0.95. Then take 1 minus the 0.95, and you get 0.05. And that is going to be called your alpha level. So we're going to have 95%. We're going to make that into a proportion. So we're going to have 0.95. And then we're going to do 1 minus that and get 0.05. And then so 1 minus your confidence level equals your alpha. And then you have to divide the alpha by 2 because we have 2.5% on one side and 2.5% on the other side. And so we're going to get the 0.025, and we're going to look that up inside the table, because the probabilities or the percentages or the proportions are inside the table and the z's are on the outside. So we're going from a probability and we're going out to the z value. So I'm going to find it. and it is right here. And then you're going to go out the left, and we're going to get a negative 1.9, and then go up to get the second decimal place. Remember, this is the second decimal place, and the first column gives you the whole number and the first decimal place. Okay, so then we get negative 1.96 as our critical Z. And then because the normal distribution is symmetric, the other one would be 1.96 if you look that one up too. So you can just look up the negative one version because that's the easiest to get. Okay, so now we have our Z, and we found our sample mean, and we're going to make the confidence interval. So we're going to use that Z for our confidence interval now. And so this Z tells us that from our sample mean of 80, where negative 1.96 standard errors from the sample mean. So the Z is in standard errors. So whatever our standard error is, which we need to calculate based on the central limit theorem, then we go out 1.96 standard errors to the left and to the right, and that is going to be our margin of error. All right, so hopefully you kind of got along this far, but let's just talk about it a little differently, what a confidence level is, and if you kind of just memorize this, you'll be fine. Hopefully for those who really like stats, you kind of understood what I said before, it kind of started to sink in. But hopefully at least you understand the slide, if anything. So say now we have a 90% confidence level instead of a 95. So if we randomly selected 10 samples in of the same sample size and made 90% confidence intervals for each of those samples. So we have 10 samples, we make 90% confidence intervals, then you expect that 9 out of 10, which is 90%, would obtain the true population mean. So say this true population mean, which is in green here, I'm going to call mu. We don't know what it really is, but we make 10 confidence intervals based on the same sample size. We would expect that 9 out of 10 of them would contain the true population mean, which is something we don't really know, but 9 out of 10 would contain it. So the blue ones are the one that contain the true population mean, and the red one does not. So confidence level is not about one particular confidence interval, because we don't know if it really contains a true population mean or not. We don't know. We don't know if we have a blue confidence interval or if we have a red one. We don't really know when we just take one at a time. But what we do know is in the long run that about 90% of the confidence intervals that we calculate will contain the true population mean as long as the central limit theorem holds up. So you can't put too much weight into just one confidence interval. You really need a bunch of them to really make any really sound statement. But you know, one is going to be pretty good as long as you have a good sample and a big enough sample size. But the key is that in the long run, if you have 90% confidence, then about 90% of the confidence intervals will contain the true population mean. But again, you don't know which one does and which one doesn't. You don't know which one's the wrong one. You don't know if you have a red or a blue one at any given time. Unless somehow you know the true population mean, but then you wouldn't be doing a confidence interval to estimate it. So how how do you calculate the confidence interval? So I'm going to go to the formula. So for a mean, we're trying to estimate the population mean. So for that, we're going to have the sample mean plus or minus our margin of error. And so you're going to have a lower bound, which is the sample mean minus the margin of error. And then you're going to have an upper bound, which is the sample mean plus the margin of error. And the margin of error is, again, it's based on the z, which is our confidence level. It's determined by our confidence level and the standard error. Okay, so we're going to multiply those two things. And the standard error, which is the standard deviation of the sample means, is the population standard deviation divided by the square root of n. So if we kind of put that all together, then we're going to have this sample mean plus or minus the standard deviation divided by the square root of n, the sample size. So we're going to have a lower bound, which is the sample mean minus the standard deviation divided by the square root of n. And upper bound, which is the sample mean plus the standard deviation divided by the square root of n. So this is the formula in multiple ways. And here are the steps to calculating confidence interval. So first you want to check the central limit theorem to see if it holds true, because if we don't know about the central limit theorem, if we don't know it holds true, then we can't estimate the standard error. And that's crucial. Because if we can't estimate the standard error, we can't put a margin of error on it. And then we don't know how confident or how precise our confidence interval can be. So you need to make sure that is true first. And if it's true, then you can find the standard error. And you can find the critical z based on your confidence level. And then multiply those two things, the standard error and the z, to get your margin of error. And then do the sample statistic minus the margin of error to get your lower limit. Then have your sample statistic, your sample mean, plus the margin of error to get your upper limit. And then you want to interpret the confidence interval. And to interpret it, you want to say something like this. So with whatever confidence you have, 90, 95, 99, could be other confidence, but you want to keep it high. So with whatever confidence, I expect that the population mean of whatever you're talking about is between your lower bound and your upper bound. So you're just going to kind of fill in the blanks here. Here are some common critical z's. So remember I said 90, 95, and 99 are the most common. So if you have 90% confidence level, your critical z will be 1.65. If you have a 95% confidence level, then your critical z is 1.96. If you have a 99% confidence level, then your critical z is going to be 2.58. So in this class, these are the only three you're going to use, and probably these are the only ones you would ever use, unless maybe you're in a different field. But in psychology, at least in psychology, the most common and the one you're going to calculate the most amount of times, like probably 99% of the time, is going to be the 95% confidence level. And so 1.96 is something to keep in mind. Try to remember that one. The most common in psychology. So let's do an example. So let's create a 90% confidence level for a sample mean of 80 exam points. So say we have a class and we want to estimate the true population mean for this class. So I want to know, for say of all statistics, what's the true population mean. So I mean, for anyone who's going to take this class or who has ever taken this class, what is the true population mean? But I don't know it, and I can't really calculate it because that's a lot of people, and I'm not going to have all the data for it. So I might take, say, this class and calculate a 90% confidence interval. And say, hypothetically, I get a sample mean of 80 exam points. And somehow I know that the population standard deviation of exam scores for this class is 6 points. Now, sometimes knowing the population standard deviation is not really something that we have, and it's something that most of the time you're not going to have unless it's like the ACT scores or something like that, where they keep all the data that they ever have, and you can be pretty sure that the population standard deviation is some certain amount. But most of the time you're not going to really know it, and that's what we're going to talk about next in the next video about the t-distribution. But let's just say for now that we know somehow that the population standard deviation of exam scores for this class is 6 points, but we don't know the population mean, and we take a sample of 36 students and we estimate their sample mean to be 80 points. So let's go through all the steps for our example problem. You want to check if the central limit theorem holds true or not, because if it does not hold true, then you can't estimate the standard error, which is number 2. If you can't estimate the standard error, then you can't do the problem. And also, if it's not a normal sampling distribution, according to the central limit theorem, then you can't use the z-table because the z-table is only for a normal distribution. So if the central limit theorem doesn't hold true, we can't do 2 and 3, and then we can't do a confidence interval. But if it's, approximately true, I guess, you're pretty confident that it's true, then we can do the problem. Or at least you can note that it might not be 100% accurate, but it's pretty close. So for it to be true, we need a normal population distribution, or the n has to be at least 30 or more, and we need random sampling. So let's see if that is true for our example. So I don't see anything in the problem about the population distribution. So the population distribution, again, is the histogram of individual scores. I don't in the population. So that's everyone, not just my sample. I don't know about that from this problem, from what is written here. From my experience, usually scores for my class are skewed to the left. So this is probably not true, and I don't really know if it's true or not. So that's probably not true, but we do have an N of 36 because there's 36 exam scores. So I took exam scores from 36 people. So our sample size of N is 36, and that's at least 30. So if we have random sampling and our N is at least 30, we can be pretty certain that we have a normal sampling distribution. And if we have a normal sampling distribution, then we can estimate the standard error from the sample size and the standard deviation if we know that, and we can use the z-table. But for that to be really true, we need to have random sampling. It doesn't say anything about that it is a random sample. It's not, because we're taking 36 exam scores from this particular one class, and I really want to know about all my classes. And I'm not randomly sampling from all my classes. I'm only taking some people from my one class. So it's not a true random sample. But hopefully, at least the sample is somewhat representative. It's not biased in some obvious way. So my confidence interval is not going to be like perfect, I guess, or my confidence level might actually be biased. Well, that's what's going to happen is your confidence level that you state is not going to be 100% true. It's not going to be exactly like 90% in this example. It's going to be off. I don't know if it's off which way. I don't know if it's lower or higher, but our confidence level is probably not going to be exactly 90%, but hopefully it's not too far off. Now, if I purposely went and sampled the students that I knew were smart or usually do well in my class, then you're going to really bias your confidence level. Or if maybe this class was full of AP students in high school, maybe this exam score is going to be off too. I mean, maybe they're really smart and they have higher exam scores, or maybe because they're in high school, this is too much for them and they have lower. So you just want to make sure that your sample is pretty representative It's not going to be perfect, and you're going to need to note that, but you still continue and hope that at least it's pretty representative, okay? So then we go to number 2, because this central limit theorem holds up for the most part. We know it's not a random sample, but we're going to say it's good enough. Oops, right, going that way. And so we're going to get our standard error. And our standard error is our standard deviation divided by the square root of n. And so our standard deviation from the population is 6, because it's stated in the problem. And right here, and then we have an n of 36. We had 36 exam scores, we had 36 people, so our n is 36. The square root of 36 is 6, so 6 divided by 6 is 1. Our standard error is 1. Our standard error is the standard deviation of the sample mean, according to the central limit theorem. And we said it's pretty true, so we're going to get a standard error of 1. And then also, because the central limit theorem holds true, we're saying that the sampling distribution is normally distributed. So we can use the normal distribution table, which is our z table. So we need to find that. So go to the table again, and we had a 90% confidence level, so our critical z is 1.65. Okay, so let's go back to our problem here. We have a z of 1.65, and to calculate the margin of error, we're going to take the critical z times the standard error. So we're going to have 1.65 times 1, which equals 1.65. So our margin of error, mo, is 1.65. We want to calculate the lower limit, which is our sample mean minus the margin of error. So we're going to have 80 minus 1.65, and we're going to get 78.35. Then we're going to find the upper limit, which is our our sample mean plus our margin of error. So we're going to have 80 plus 1.65, which equals 81.65. Then we want to interpret the confidence interval and write a sentence. So we're going to fill in the blanks. So with 90% confidence, I expect the population mean of exam scores to be between 78.35 and 81.65 points. Notice I included the confidence level, because if it was a 95% confidence level, the ranges would be further apart. We would use 1.96 instead of 1.65 as our critical z, changing the number. So you want to make sure you have the confidence level there. And then we're estimating the population mean, not the sample mean. We're using the sample mean to estimate the population mean, but we're making an inference about the population mean based on our sample mean. And an inference is a statement about the population based on our sample. This is why we're doing inferential statistics, inference. And so you want to say population mean, and then you want to say what you're talking about. In this case, it's exam scores. And then you want to say it's between your lower bound and your upper bound. Make sure you include some kind of units, and in this case, it's just points. But make sure you say units, because if you're talking about time, if you don't put the units, I don't know if you're talking about seconds or hours or whatever. So make sure you put the units. And so there is our example. So it's not that hard. Understanding the concept is kind of hard, but actually calculating it is really not that hard. And writing this sentence is really not that hard. All right, there you go.